Hi class. So you should have finished already with the first video. I hope you enjoyed that awesome energy that he always makes sure to bring to his lectures, and hopefully I won't bore you too much with talking about phase change diagrams. And so just recapping, we have solids, which are nice and ordered. They have strong intermolecular forces. As you add heat, then they start to space out a little bit more. They can move a little bit more freely or to flow, as he said. And then, if we add even more heat, this is where you get the most movement. And so I'm really going to talk about this change of phases a little bit, but we first need to talk about a couple definitions. That being, when you need to add energy into a system, so for example, going from solid to liquid or liquid to gas, that is considered endothermic. But remember, we also talked about processes of going, for example, back from a liquid to a solid. This is exothermic because you are releasing heat into your surroundings. So this is what we call for the release of heat from a system to its surroundings. And so we're going to talk briefly about heating curves. And so this represents this process that's happening, and we can actually assign numerical values to them. And so first is we start off in our solid phase. So our solid phase is going to be, for our heating curve, is going to be times 0 on the left bottom part of the graph. And so what's going to happen is, as time goes on, think of as time is increasing, we are adding heat. And so as time goes on, we start adding heat. These molecules, they're now going to start vibrate a little bit more, until we reach the melting point. So here, where we see an increase of change, this is representing kinetic energy. The reason why we see a plateau at the melting points and the boiling points has to do with this is strictly just a transfer of potential energy. There is no change in kinetic energy. The temperature does not change while the solid is changing to a liquid or liquid to gas. And so once all of the solid becomes liquid, we keep adding heat. This process happens where we break a little bit more of those intermolecular attractions until we get to the boiling point. Here again, just a transfer of potential energy until the liquid turns into gas and they are in their most movable phase. And so it's really important to understand that, one, these changes are endothermic, going from solid to gas as we're inputting energy. And so we start to understand a little bit about each of these phases. And when I tell you that this first plateau here, I'm going to pull this out of the graph so it's easier to see. This represents a term that's called heat of fusion. And so this represents an amount of energy. So these are in units per joules, which is energy per gram. So how much energy it takes to turn something from a solid into a liquid. And then this plateau represents what's called the heat of vaporization. So again, units of joules of energy per gram. So it tells you how much it takes to break that final last bit of intermolecular forces we have going on. And so here I want you to answer the question that I have here. So go ahead and pause and rewatch if you need to. But again, this has to do with it's strictly change of potential energy, not kinetic. And so what I want you guys to do now is practice analyzing a heat curve for water. And so we have it going from 200 Kelvin to 400 Kelvin, or which is the same as negative 73 degrees Celsius to 127 degrees Celsius. And so just a reminder, if you're not familiar with this relationship, is that Kelvin is equal to degrees Celsius plus 273. And so that's how I got those numbers there. And so what we should see is that this melting is at 0 degrees C, or our melting point, which in Kelvin is 273 K, which is where this line represents. And then we know that water boils at 100 degrees Celsius. And so this should be at 373 degrees, which is where we see the segment from D to E. And so what I want you to do is practice interpreting this. So pause the video and answer the following questions I have on this page. And when you're done answering them, unpause, and then I will go through it with you. All right, first question here. It's asking how many minutes pass from the first appearance of the liquid phase until it's entirely into the gas phase. So the segment that we're talking about is when it first appears in liquid, right here. This is where we're just getting an introduction of liquid. Because remember, during this plateau, you have both a liquid plus a solid. So B is where we're going to focus as our beginning. And so if we look where this lines up at 4 minutes. Now, if we're going till the substance is entirely into the gas phase, that means we need to get through the whole entire boiling point section. So that brings us to part E of the graph. And so if we follow that line down, that brings us to 34 minutes. And so then you just have to calculate the time difference here. So 34 minus 4 is equal to 30 minutes. How many minutes will it take for water to undergo melting? Well, here, the solid starts to melt again at B. So we're starting with segment B, which we already know is at 4 minutes. And then for it to completely undergo is going to point C. And C lines up at 8 minutes. The difference between 8 and 4 is 4. And so that's how long it takes for water to undergo melting. Oops, I knew I wasn't writing something there. Okay, minutes. Perfect. All right, next question. How many minutes is the water completely made of a crystal lattice? So there's a couple parts here. One is remembering when you see crystal lattice, that's the solid phase. When they're the closest together. And so the segment that we're looking for is going to be where it exists as just a solid, which is between points A and B. Well, A starts at 0 minutes. B, again, 4 minutes. And so really, it only lasts again 4 minutes in the solid phase. The lone solid phase, I should say. What line segment represents when water is both in liquid and gas phase? So again, if we're looking at this heating curve, we start with a solid, then we are into this liquid-solid mixture till we're completely liquid. And here, between D and E, that's where we have our liquid gas at our boiling point. So it'd be segment DE. That's how you write it, right? It's been a while since I've done segments in math. How many minutes will it take for the water to boil once the boiling temperature is reached? So here, as first we have to find where the boiling temperature is reached. In our case, that's D when it first gets there. And so this segment represents how long it takes for the water to boil. So we're going from D to E. Well, D is at 20 minutes if we follow that down. So D, 20 minutes. And then E is at 34. So here we take 34 minus 20, which gives us our 14 minutes. And so what I wanted to talk about specifically with water is that, remember these terms that I was telling you about the heat of fusion? Well, for water, that's equal to 334 joules per gram. However, its heat of vaporization is equal to 2260. I'm going to move this over here. Joules per gram. And so what this means is if you have 1 gram of water, to get it to melt, you have to put in 334 joules of energy. And if you also have 1 gram of water, you have to put in 2,260 joules for it to boil. And so keep in mind that this takes less energy for the fusion versus vaporization is about 8 times more, which should make sense because here you are interrupting some of the attractive forces, but this energy is how much it takes to overcome the attractive forces completely until it's into the gas phase. So these are things that you can compare between substances, and so I just wanted to bring your attention to that. But that's all I had for today, so hope you enjoyed.